Hello and welcome to Earthquake Tip number 10. My name is Dr. Shailesh Kumar Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to understand language to our professionals who are in the field designing and constructing structures, especially architects and engineers. Before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. The earthquake tip number 10 is on how flexibility of buildings affects their earthquake response. If you remember, the importance of ductility was discussed in last tip, and now let's understand the flexibility, that is back and forth motion of building during earthquake and how does it affect the performance of building. It is now known to all of you when ground shakes due to earthquakes, the base of building moves with the ground, whereas the building swings back and forth. If the building is rigid, then every point in the building will move by the same amount as the ground. However, most buildings are flexible and different parts of building move back and forth by different amounts. Let me explain you by the example. Look at this figure. Let us take a thick wire rope and tie its one end to the roof of a building and its other end to a tractor. Next, start the tractor and pull the building. The building will move in the direction of pull, as you can see in this figure 1a. For the same amount of full force, the movement will be larger for a more flexible building. Now let's cut the rope. The building, once the rope is cut, will oscillate back and forth horizontally as shown in this figure 1b, and after some time come back to its original position. Graphically, these oscillations can be represented as shown in this yellow graph, and they are periodic in nature. The time taken in seconds to complete each cycle of oscillation, that is one complete back and forth motion, is the same and is called fundamental natural period and denoted by T of the building. The value of this T or fundamental natural time period depends on building flexibility and mass. More the flexibility, longer is T. Also, more the mass, longer is the T. In general, taller buildings are more flexible and have large mass and therefore have longer fundamental natural period, that is T. On the contrary, low to mid-rise buildings generally have shorter T, means low-rise buildings are comparatively rigid. Now let's look at this figure number 2, which gives you examples of natural period of different structures. The fundamental natural period T of normal single-story to 20-story building are usually in the range of 0.05 seconds to 20 seconds. This time period is inherent property of building, and any alteration made to the building will change its T, that is fundamental time period. Now let's understand the importance of flexibility. And for that, we need to first understand how the ground motion is transmitted to the building. And this is being explained through this figure. The ground shaking during earthquake contains a mixture of many periodic, that is sinusoidal waves of different frequencies ranging from short time period to long time period, as shown in this figure through red, orange, and yellow colors. The time taken by the wave to complete one cycle of motion is called period of earthquake waves. In general, earthquake shaking of the ground have waves whose period vary in the range of 0.03 to 33 seconds. Even within this range, some earthquake waves are stronger than the others. Also, the intensity of earthquake waves at a particular building location depends on number of factors such as magnitude of earthquake, epicentral distance, and type of ground, etc. Now let's say in a typical city, we have a building of different sizes and shapes. And one way of categorizing them is by their fundamental natural period, T. As shown in this figure 4A, the ground motion under these buildings vary across the city. If the ground is shaken back and forth by earthquake waves that have short period, the short period buildings will have larger response. Similarly, if the earthquake ground motion has long period waves, and long period buildings will have larger response. Therefore, depending upon the value of T of the building and on the characteristic of ground motion, that means the period and intensity, some buildings will be shaken more than the others. Let me supplement this by an example of 1967 Caracas earthquake in South America. The response of building was found to depend upon the thickness of soil underneath the buildings. This is shown in figure 4B, which shows that buildings up to 3 to 5 story tall, the damage intensity was higher in areas where underlying soil cover was around 40 to 60 meter thick, but was minimal in areas with large thickness of soil cover. On the other hand, damage intensity was just the reverse in case of 10 to 40-story buildings. The damage intensity was more when the soil cover was in the range of 150 to 300 meters and small for lower thickness of soil cover. Means soil cover under the building plays the role of a filter, allowing some ground waves to pass through and filtering the rest. If the period of building matches with the period of filtered ground waves, the building will suffer damage, whereas others will not in the same locality. Let me also tell you here that flexible buildings undergo large relative horizontal displacements, which may result in damage to various non-structural building components and the contents. For example, some items in the buildings like glass windows cannot take large lateral movements and are therefore severely damaged or crushed during large shaking. Similarly, unsecured shelves, almirahs might topple, especially at the upper stories of multi-story buildings. These damages may not affect safety of building, but may cause economic losses, injuries, and panic among its occupants. With this, we come to the end of this earthquake tip number 10. You can download this tip from www.bmtpc.org website. The next earthquake tip number 11 will be on what are the Indian seismic codes. Thank you.